so if x minimizes this integral, makes it smallest it can be. Oh, with these points fixed, the rings are given, right? So we're not changing them. Then it turns out, well, then it satisfies the Euler-Lagrange equation, which I'm not going to write because it's not instructive. It doesn't explain anything. But what's interesting is that I don't know if people know what that, well, it turns out that x is a catenary, then x is a hyperbolic cosine. So it's, well, with coefficients, right? So cosh of x with some coefficients which depend on this point. Let us, so I don't want to write the Euler-Lagrange equation, but I want to make a couple of remarks. So remember I said that if, well, you see our function L, so in this case, L of x and x dot in this case is just x multiplied by the square root of 1 plus the derivative squared.
They're asking if there is no hyperbolic cosine of t, maybe, yes?
I'm sorry, of t, thank you so much, yes. Hyperbolic cosine of t, maybe t over a times a, some, so there is a one free parameter. And what I wanted to mention was this. So if L was the difference of kinetic and potential energy, for mechanical systems, we had conservation of energy, which was expressed as follows. It's x dot differentiate L by x dot minus L. That was a constant along any solution of the Euler-Lagrange equation that is generated by this L, right? So along any solution x of t. So it doesn't depend on t when you plug a solution in. What is, so in the case of mechanics, this is the total energy. So if L was mx dot squared over 2 kinetic energy minus potential energy, then let's call it H, right? Then H is the energy. Then a simple calculation, which I will skip, you can just plug L into this expression and do the simple calculation, and it turns out it's the only thing that happens is plus appears instead of minus. So that's the energy. So in this case, it's a physical interpretation. What is the geometrical or any other interpretation in case of the Lagrangian coming from the soap film? If this is the Lagrangian, what is this? And something, in other words, doesn't depend on t in this picture. So if I pick any value of t, something doesn't change. What is it? It's certainly not energy because nothing is moving. And it turns out that it is the horizontal component of the surface tension. It is simply Newton's first law. In other words, if you look at the soap film and you cut it here, and instead of this soap film, you replace the stuff to the right by a tension, you know, my picture is two-dimensional, but if I drew it in 3D, it would be like this. So you cut off the film to the right, but you hold this film by the kind of tangential forces, right? Kind of a cone of equidistributed force. So if you project this force onto the on the t-axis, that is exactly the geometrical or physical interpretation of the conserved quantity. And it's clear that it has to be the same, because if I cut the surface in some other place and replace, so I remove everything, if I remove everything here and here, so I look at the forces that pull it to the left, because this piece of soap is in equilibrium, horizontal forces left and right must be equal to each other, and that's the simple interpretation of the conserved quantity. So it's interesting how the same mathematical expression has utterly different meanings. In the dynamics, it's in total energy. In the statics of the soap film, it's the horizontal force. So that's one remark I wanted to make. The conserved quantity has different interpretations. The second question is purely mathematical. Under what conditions, and by the way, this took 50 years for people to figure out. And so we look at this integral from along the minimizer and ask ourselves, let's say L satisfies the Euler-Lagrange equation. Let X satisfy the Euler-Lagrange equation. Can we guarantee that of all the curves, this particular graph gives the minimum? And Legendre said, so let me write the question down. So is such X guaranteed to be a minimizer? Well, a similar question in calculus. If a function has zero derivative, which is basically what the Euler-Lagrange equation is the analog of, it's kind of saying that this functional has a zero derivative at this quote unquote point. Of course, you wouldn't expect it to be a minimizer, like in vector calculus. Some kind of a second derivative has to be positive. And Legendre said yes, it's a minimizer if L differentiated by the second variable, second derivative of L with respect to X, is positive. And so, for example, let me give you a simplest example. Let's take L to be just the difference of squares of X dot squared minus X squared dt from, let's say, 0 to some number A. So according to, so let's look. So this is our L. So L differentiated with respect to X dot twice is just what? It's 2, right? It's a second derivative with respect to the of X dot squared minus X. Again, we are not treating X as a function of time. We're treating X and X dot as independent variables. So this is just 2. It's just 2, so it's positive. So according to Legendre, let me actually take even, I need to prescribe the endpoints, right? I didn't say anything about the endpoints of this function, right? So let's assume that they're 0. And so in other words, let's take the endpoints, this and A. Okay, so according to Legendre, well, you can write the Euler-Lagrange equation. You can write the Euler-Lagrange equation. Let's see what it is. We kind of can guess because this is potential kinetic energy, and this is potential energy is x squared. That's for Hookean spring, right? Hooke's spring has potential energy kx squared. In this case, or over 2, it doesn't matter. So Euler-Lagrange equation is so L sub x dot equals to just x dot twice, right? And L sub x equals to minus 2x, right? I simply differentiate, and then Euler-Lagrange says that d by dt, I cancel 2, so it's of x dot minus x, right? Equals 0. So in other words, x double dot plus x, it's a harmonic oscillator. And so, of course, a harmonic oscillator has 0 solution. If you clearly 0 solution satisfies the differential equation, and it satisfies the boundary conditions. So, however, Legendre made a mistake. It's very strange. I'm surprised. I often wonder if it's not. Maybe he just was careless. But anyway, people say that he made a mistake. This is a false statement. It's a necessary condition for the second derivative to be positive, but it's not sufficient. For example, take a equal to, let's say, 2 pi. So if a equals to 2 pi, then so here's xt, here's 2 pi, here's pi, and the solution, okay, there is a 0 solution connecting with these boundary conditions, but there is also infinitely many others, sines with any amplitude. So these are different solutions, right? And so, are they the same length? Yes, it turns out that they have the same length. So certainly this is not, well, it is a minimizer, but it's not a unique one. But if I take a is less than 2 pi, so here's 2 pi, and I take a to be here, then the solution will be, we have, then this is still a solution of the Euler-Lagrange, and it satisfies the boundary conditions, but it's not the shortest curve. There is a shorter curve than this. For example, I can take a solution like this and then go straight, and this actually turns out to be the same length, but if I smooth it a little bit, then it gets shorter. So in other words, it's not a minimizer of this integral. So that's Legendre condition is necessary, but not sufficient. So let me just say 50 years went by after Legendre. And then Jacobi found a sufficient condition, which is actually, together with Legendre, is necessary and sufficient. So exactly what's needed for the solution to be minimizer, and the Jacobi found the answer. And let me just show it geometrically. So instead of, so the Jacobi condition says, I'll say the words, but then I'll draw a picture which explains the words. Jacobi says a sufficient for minimality, right? For x to be a minimizer, to have no conjugate points. I'll say what they are and give an example with a projectile and with a soap film. To have no conjugal points between, in this interval in question, in the interval from T0 to T1. So what is a conjugate point? So let's say here is T0, T1, and we found a solution to the Euler-Lagrange equation that connects these 2 points. How can we tell if it's a minimizer, if this is the shortest solution, at least shorter than its neighbors, than all its neighbors? Here's the answer. Take other solutions of the Euler-Lagrange equation near it. So take different solutions with the same initial value, but with different initial slopes. It's a second order ODE, and the solutions can behave like this, right? So you see these nearby solutions may or may not cross the main solution. And if they cross, that is, as you basically you take this angle alpha. As alpha goes to 0, this point, if there is an intersection point, approaches to some limiting point. If that limiting point is in the interval, then it's a conjugate point. So in other words, the conjugate point is where the nearby trajectories focus, okay? And you see in this example, here's the starting solution, and these are nearby ones. You see, and the pi is the first conjugate point. And there are, of course, all of these other are also conjugate. But there is no conjugate point between 0 and pi. And therefore, in this case, if I take a to be here, then the integral from 0 to this a is minimized by this solution. Any other curve will give us a bigger value of the integral. But as soon as you take a at another place, if you take a here, then this is a solution of the Euler-Lagrange equation. This is 0 solution, but it is not the shortest curve. Okay, so here is an example from real life. Where
Can I make a question?
Sure, thank you for asking.
I know that this theory is for weak minimizers.
Yes.
So yes, so but the theory is different from strong. Is it for strong minimizers?
That's right. So this is only for local. This is a local criterion. It's
Okay.
like, yeah. This is only for the curves that are near the one in question. So it's like the second derivative. It's exactly like the second derivative test from calculus.
Yes, thanks.
It doesn't tell us anything about global minimum or maximum.
Okay.
Thank you very much. Yeah, that was a good correction. Yeah, so let me show you a kind of a, I apologize again if you already knew this, but I didn't until not that long ago. So let's look at the projectile. So we are at the origin and we shoot a cannon at different angles, and you see this envelope of safety, right? If you shoot with the same speed from the same point, and the trajectories look like this, and here is the envelope. I'll dare to use red color. Maybe I'll just erase this and draw the envelope in red. So this is, it turns out to be a parabola also, but of course of different shape. Okay, so this is one of the beautiful things that I don't have the time, but it's Maupertuis's principle says that if we fix the energy, which is the case here, right? Here we shoot with the same initial velocity, speed. So all the trajectories drawn here have the same energy, same total energy, because their starting energy is the same and the total energy doesn't change in flight. So So if we fix, so this is Maupertuis's principle, which was proven, first discovered by Koenig, and a decade or two later was proven by Euler and was given Maupertuis's name. So this is a common injustice. And so fix energy, fix total energy, then trajectory. So I'm talking about this flying projectile, but this applies to any motion in a potential field, in a conservative field. So then any trajectory minimizes, or I should say extremizes. Well, let me say minimizes, but in quotes. It is true that it minimizes if the endpoints are close enough to each other, and I'll describe this. So I'll put in quotes minimizes, not the length, of course, because that would be then no gravity, right? But the integral of speed times arc length over the curve gamma. So here's the picture. So if we have 2 points, A and B, and we shoot from A to B with that fixed energy E, which doesn't change in discussion, then the curve gamma minimizes this integral. So that kind of explains, well, explains is the wrong word, why the trajectory is bent upward. If you want to go from A to B like this, the trajectory bends up. That is because the speed is less there, right? V, I should say that the speed is given by the conservation of energy. So it's mv squared over 2 plus, in this case, mgh, right? The potential energy equals to E. So in other words, V is a function of the height. In more general potential, it's a function of position, right? So if we know the total energy and we know the location, then we know the speed. So it's like a Riemannian metric. It becomes a differential geometry problem, right? Finding the curve which minimizes the length measured not in the Euclidean sense, but in this sense. Okay, so the question is, if I pick a point B, so let's call this O, and this is A, OA. I want to know, I can shoot, you see, I can shoot at A like this, or I can shoot at A like this, right? We can hit with a cannon. If it's behind a building, then you can shoot like a mortar shoots, right? Which of them is minimizing? So each of these are, both of these curves are stationary. They satisfy the Euler-Lagrange equation for this. You see, I should mention that this is, notice that this integral is of the kind we discussed. So V is a function of, and because there is no time, let me call this T and this is X, right? I just want to keep always the same notation. Time doesn't play a role in this problem. We're only talking about the trajectory shapes. We're not saying how. So V is a function of the height, and the arc length ds is what? It's 1 plus x dx by dt, that is the slope, right, squared dt. This is the integral, right? And if we're talking, let's say this point has x coordinate a, so it's the integral from 0 to a, right? So we want to minimize. You see, this is exactly of the kind, it's an integral of the function of x and x dot. So I'm bringing this up as an example of the general integral. but very palpable. And here it turns out that the straight shot, so to speak, this parabola makes this integral minimal. And why is that so? Because there are no conjugate points. Because if you shoot a little bit above or a little bit below, you get these trajectories. You see, none of them intersects this parabola before, right? So this is the minimizer of this integral, while this isn't. And why is not? Because if I, let me draw it without messing it up. So here's this. And if I take nearby trajectories, you see they must cross. So there is a conjugate point. In fact, the conjugate point lies on the envelope. You can kind of see it from this picture, right? So that's kind of nice. So this envelope, this red curve, is the set of conjugate points for different trajectories. And if, yeah. All right, so that's one thing. I probably should not, there is an interesting story also with the soap film. For example, you could ask, how far can you take these rings apart before the soap snaps, right? You can answer this. And also, let me just say very quickly. So here are these two rings on which the soap film is stretched. So this is a kind of a cross-sectional view. And okay, well, this is the physically observed soap film. That's the one which minimizes potential energy. If it didn't minimize, you would not observe it physically, right? It would be unstable. But there is also another one that is not observed, and it's more steep like this. I thought I sent Stefanella my notes, but apparently they didn't go out. So I'll send them again, and this discussion is in detail in these notes. So I will not do it because otherwise we don't have the time to do the rest. Okay, so that was, to summarize what I said so far, is the Legendre condition, which is necessary for a minimizer, the Jacobi condition, which is together with the Legendre necessary and sufficient for a curve to be a local, also called weak minimizer. Okay, and a couple of examples from, yeah. And I thought maybe I will also mention, so the main thing I wanted to describe was this point of view which explains where the main concepts from Hamiltonian mechanics come from. And I don't want to kind of make it a little too sudden. So I thought maybe I'll give another example, which is of interest in its own right, I think. So we looked at the first thing I said last time, I think one of the first was, we look at the Lagrangian, which is the difference of kinetic and potential energy. And this is kind of a little bit unpleasant because what is the meaning of this difference? And it kind of bothered me too. And then I thought of a partial, I don't know if it's satisfactory, but something that has exactly a direct physical interpretation of this quantity. So what is this thing? It seems meaningless. Adding, yes, but subtracting. So here is the thing. I have to take my, yeah, I don't know if you can see me. If you look at this link here, right? So let me hang it. This is a two-dimensional problem. I want to show the quintessential, the basic, the simplest version. So look at this slinky, right? I claim that potential energy of this slinky is given by this formula, which is, so this is integral from, let's say, T0 to T1, doesn't matter. And here is the integral of exactly this kind. So what I want to potential energy of the slinky of course, I have to make some simplifying assumptions. So first of all, let's say X is the vertical direction. Let me do the analogies. So T here, in this case, T is the time, and X of T is position at time T. How would we describe the configuration of the, I'm thinking of this as a one-dimensional object, okay? How would we describe the elongation of the slinky? We should say, the most natural thing is to measure the mass. Let's say from the top to bottom, right? It doesn't matter, or from bottom to top. Let's measure the mass from one end. So let's call it, I don't want to call it T, or should I? I don't know what's more confusing. Let me, so here's the piece of this string. This is the whole string, right? X is the vertical direction. And here I measure the mass of this piece as, call it, okay, let's call it mu, all right, so that we remember, okay? I don't want to call it M because M is in the dynamical problem. So that's the mass, mu, and what is the range of mu? Mu goes from 0 to the total mass, right? That's the capital M is the total mass of our object. X of mu is the location of the particle which bounds mass mu, right? So X of mu. So X of mu, let's call this position X0 and the final position X1. X of mu, well, it varies between X0 and X1, doesn't matter. Now here's a nice, let's say I buy 1 kilo of this thing in a store, right? So let me say 1 unit of mass has spring constant, Hooke's constant, right? Call it K. Okay. So that means if I stretch it, and my slinky has 0 length when it's not stretched, right? So the tension is going to be K times the length, right? What if mu, d mu, a small unit, if I take a small piece of this, d mu, mass has spring constant if I cut this in half and ask how stiff is the half compared to the whole, what do you think is the spring constant of half? It's going to be stiffer, right? A short piece You see, you want to stretch the short piece by the same length as the long piece. It's harder because each link has to be stretched more. Each spiral unit has to be. So in other words, the smaller the mass, the stiffer it is. So the spring constant will be the K divided by d mu. So if d mu is tiny, it's an extremely stiff spring, right? It makes sense, right? If you take a rubber band and you take a cut off a tiny piece of the rubber band, it's very difficult to stretch. Okay, so this is a spring constant. What is the potential energy of stretching? Of the mass d mu. What's potential energy of any spring? For any spring, it's 1/2 kx squared, right? 1/2 k times the elongation. So it's going to be 1/2 times Hooke's constant, which is k over d mu, times the elongation squared, which I call dx. So it's length. It has 0 length if you don't pull it. When you elongate, I call dx. So, okay. So now, finally, what's the potential energy of the whole thing when I stretch it? It's the sum, which means the integral of yes, so the sum is going to be the integral. T goes from 0 to m. I'm sorry, mu goes from 0 to m. And I'm simply substituting this, right? I'm adding these things up. It doesn't look good, but it will be perfect in a second. 1/2 k over d mu. And dx is what? The only thing I have to say, dx is basically x of mu plus d mu, right? This is the location. This is the location of the point to the left of which the mass is this, right? Minus x of mu, right? Which is approximately equal to x dot squared of mu times d mu, right? And that's what I plug in here. So it's x dot squared d mu. I'm sorry, not squared. Yeah, the square is here, right? So I have x, no square here. This is x of mu. I plug this in here. So we get d mu squared. And you see d mu cancels, and we have a normal looking integral. It's the integral from 0 to m of 1 k x dot squared over 2 d mu. So you see, it's exactly the same formula as in the dynamical case. But I still, so this, what I wrote so far is the energy of stretching. And by the way, this formula doesn't insist that x is, I mean, I could forcefully hold it, you know, stretched in some parts and compressed in others, whatever I want to do. This formula gives me the potential energy of stretching or of stretching for any stretching pattern. And I should have included gravity. And what's gravitational force? That would be an additional, what's the gravity? Gravity is potential energy. It's, let me not call it V. That's potential energy of the unit mass right, times the mass we have, d mu. That's this is the potential energy of the little piece of this thing, right? The piece d mu has potential energy proportional to its mass times the potential energy that one unit of mass would have at that location x, right? And so the total energy of my slinky is this. And now my point is that, look, I mean, it's exactly the same expression here and here. The only difference is plus and minus. So to summarize, if I maybe made some details not terribly clear, my point is that the formula comes, the same exact expression comes in two interpretations. It is a Lagrangian of a moving particle, or it's a potential energy, if I simply call P minus V, right? Then it's the potential energy of the slinky. And this analogy, this equivalent, it's more than equivalence. It's more than analogy. It's an exact equivalence. Now we didn't have to know any ideas from Euler-Lagrange. We could use basically common sense to derive the Euler-Lagrange equation for this. You see, we could introduce P equal to negative V. And then instead of this integral, I can look at this, but this one I can touch with my hands, and I know what minimizes this integral. So what minimizes this integral? It's the equilibrium of the slinky, right? And in equilibrium, I can just write the balance between, so here's the picture. I can write the balance. Here's my spring. I can write the force up, the force down, and the gravity. So these three things. So the force up turns out to be x dot times k force, and this is at mu plus d mu. And the force down is x dot at mu times k. And the force down is the force that would be acting on the unit mass, which is the potential energy differentiated at x, but the mass we have is d mu, it's small. So these three forces have to be in equilibrium. So if I write this minus this plus this is zero. So k x dot mu plus d mu minus k x dot, this is the down force. Sorry. Minus negative p prime of x. I'm maybe messing up. This has to be zero d mu. And divide by d mu, and you get, and take the limit, you get kx double dot equals to minus or plus p prime. Anyway, the point is, you see, we got Euler-Lagrange equation by a high school argument, basically. So I don't expect anyone to follow all the little details, but I just want to give the flavor that one can endow this meaningless integral with a concrete physical meaning, and then by just looking at it, say, well, each minimizing this integral means this thing is in equilibrium, each piece of it is in equilibrium, and when you write the equilibrium condition, Newton's first law, the sum of all forces is zero, that is precisely the Euler-Lagrange equation. Okay, so now coming back to this, when we wrote Euler-Lagrange equation, we transformed it into a Hamiltonian system, and we discovered that the area of the phase flow is conserved. That took some steps, right? We had to use divergence theorem, but let me show how you can see that the area of the phase flow is conserved without any calculation. So I need to establish analogies between the How long do I have, by the way?
Well, you know, we start late, so we still have 15 minutes or something like that.
Okay, all right. I probably should, yeah. So let me just say something that's obvious, and then if I hold this with my two hands, right? Even, let's say, so far I've talked about one dimension, but it's easier to hold it like this, and the dimension doesn't matter. So now my hands are in two dimensions, but so what, right? So I hold this like this, and if I do any cyclical motion, for example, I move this hand, or let me do cyclical uncoordinated, just give me any path in the in space here and any path there, and I make my hands trace out these paths and come back. So I do a cyclical motion. No oscillation is excited. How much work do I do? Zero, right? Because where could this, sometimes I raise it, sometimes lower it, but anyway, so I do zero work. So here's a picture. So here is this thing. Here's the force on the right hand, and here's the force that I'm applying with the left hand. And let me call the position in space. This is x1. That's in R3, right? And F is also a force. It's three-dimensional, right? And the same here, x0 and f0. And each end traces a closed path. And let me just say one thing, that note that, actually it's probably, I'll say it later. Total work, this is the key point, total work I do in executing a cyclical motion is zero. And so this work is zero. Let's write this work. So the work is done by the left hand is, so if it's the force, of course, F changes, right? So I'm not writing that dependence on some parameter. It changes, and there is a displacement x0, and this is a dot product, right? So that's the infinitesimal work the force F does over displacement dx0. So far, this integral just means physically I add them up, right, over the cyclical motion, plus the integral my right hand does the force F, the work F dot dx1. Okay, so that's the total work. I claim that this expression, I proved that the phase area is preserved and much more by this observation. Why is it so? Well, let me say it like this. So what is it for the slinky? If I hold the slinky, right? Just a simple one-dimensional case. So I hold this end and I hold this end, and maybe I pull this way, F1, and this is, I pull this one down just to be specific, right? If I'm not assuming anything, X1, X0, this is the X direction, right? So this is when I hold it like this. And let's say I just move the hands up and down only, just since that's the example I talked about, let me do it here. Still the same thing. It would be here, it would be the same thing. There is no dot product, it's just scalars. So it's integral of F0 dx0 plus F1 dx1 equals to 0. Now, what are these F0? What is the, in our case with the slinky, F what is F1, for example? F is x dot times the Hooke's constant. It makes sense, right? Evaluated at the upper endpoint, that's where capital M, right? So mass M is the mass below it, right? It makes sense. The more stretched the spring is, the stronger the tension, right? So this is the force, and X1 is X, so X1 is just X itself at M, right? And so what is the meaning of this integral? Well, you see what happens is I draw X. To be honest, we have to draw everything in a picture. So this is F, and this is X. And when I move my hand, both X and F change cyclically. So F1 and X1 change. At each stage, this is X of M and X and Kx dot of M, right? And the same kind of, and this is the area, right? Integral of dx is the area in the xf plane. And by the same token, the first integral is also the area, but in the x naught, f naught plane, which is essentially, okay, anyway, so as I move my hands, both x1, f1 change cyclically and x naught, f naught change cyclically. And at each moment during this change, to the point x naught, there corresponds a point xf. So these 2 points, you see the point in this picture and in this, they change corresponding to each other. It's one, basically, the second point is what happens to this point after time capital M. So it's a time M map from here to here. And this means that the areas are equal up to a sign. So one area is equal to the other with a minus sign. And that's essentially, that's really a very basic reason why the flow preserves area. So, and you see, this is a much more basic reason because we didn't have to write any differential equations really. We could predict, and we see directly that the reason for this preservation is that we have that everything comes well from work that I did, but what does that mean? That means we were talking about the total energy of this slinky. Anyway, I just wanted to give an illustration. You see, also here in this example, we have a mapping from 6-dimensional space to 6-dimensional space. It's such a simple thing. You hold the chain by the 2 ends, but it's a map from R6 to R6. Indeed, if you know this point and you know the force, then you, in principle, that determines, so if I know this, my left hand, and the force with which my left hand is being pulled or is pulling, that in principle determines similar data for the other end, right? So this physical thing gives us a mapping from R3, from R6, it's a 6-dimensional space, X and F, to R6. And similarly here we have, if I move this thing cyclically, then that means that I have a curve in the X naught, F naught space. and the corresponding curve in the x1, f1 space, each point of that curve, of one curve, maps onto the other curve, right? Because like I said, when I hold it still, knowing this information defines this information, right? So it's a mapping. So this information determines this information, and that's for any point. And so we have some kind of a mapping phi, let's call it. And so this, if this is a closed curve gamma, this is the image of that closed curve gamma in the six-dimensional space. And the fact that this work is zero, more precisely, we can write it now as the integral of f naught dx naught over the curve gamma equals to integral of, well, plus integral of f1 dx1 over the image of the curve. And these are dummy variables, so I don't even have to use them. Okay. Anyway, so I just wanted to say that to illustrate these ideas that later, you see, here, all this really comes to this F and this F. These forces are given by what? They're given by the total potential energy of this spring. That's one last thing I have to say. So the potential energy of this spring, of this slinky, right? The total energy. It's got stretching and elevation. I don't want to write the formula, and it doesn't matter, but let's call it S. And this potential energy depends on the endpoints, right? In principle, if I give you where the ends are, one can calculate the total energy of this thing. We call it S. And that function S of two variables, that defines everything. Because if we know S, the potential energy, I can compute the force by differentiating energy with respect to the point in question, right? So the force equals to the derivative, in this case, the gradient of the potential energy with respect to the point in question, right? Maybe with a minus sign. And so everything goes to this S. If we know S, we know F's, and we know the mapping phi. So this is from physical world. And what I want to say that if you follow the same philosophy, so I guess I will probably have to discuss it next time, but if one follows the same philosophy for the mechanics, so in mechanics, we have a similar thing. We have space, time. We have t and x. Instead of here, we are living in physical space. Our slinky is in physical space, but well, a very similar thing takes place in Lagrangian mechanics. We have two endpoints, just like we did here, and we were looking for the minimizing curve. Well, it's the same thing, right? Here we also have 2 points, and we have a minimizing curve with the integral, with the total given by S. Here, the minimizing curve and the integral over this curve is given by also by S, which is the integral of L dt, right? So that's the observation that basically, and just to give an even simpler example than the chain, Archimedes, this is where the connection to Archimedes comes in. If you look at the seesaw, just the board, and if I push the board with, and maybe let's make the board a little flexible so it's not too trivial, right? The board is flexible, it can bend. So there is some kind of a spring here, or the elastic board. And if you take the force on the left, F0, and on the right, F1, and the location, the position is X0, and the position here is X1. then we have a similar situation, right? If I know the height of this end and the force I apply, that will determine the height of the other end and the force required to keep it still, right? Again, we have a mapping from x naught and f naught to x1, f1. And in the background sits the potential energy of this bent board. That potential energy, again, I can call S, and it depends on where you hold the two ends. So it's a function of x naught, x1. And I can ask, so you see, so in this Archimedean situation, we have two things of interest, the position and the force. In the Hamiltonian case, we have, or in the Lagrangian case, we also have two pieces of information. We have a location of the particle and the velocity of the particle, or the momentum. Now and sometime later, right? And here the analog of now is this, and sometime later is this. So it's again a mapping. And whatever properties this mapping has, the mapping from here to here has. And in fact, if we simply copy the reasoning for the Archimedes to this, we ask, what's the analog of force here, right? I mean, there was no force. I mean, for now, we just have this integral, right? But what's the force on the end? What's the analog of force on the ends? It's not a real chain hanging in space. The space is one of the coordinates is the time. So what do we mean by that? Well, we have to go back to the original situation here. The force was the derivative of the potential energy. Well, so the analog of force would be the derivative of the quote unquote, not potential energy, but the action. And the remarkable thing is that, I'll just stop here, that if you look at the derivative or the gradient of this, so fix this end and look at the gradient of S with respect to this end. It turns out that the analog of force, the force has two directions, right? It's in this case, it's the t direction and the x direction. And it turns out that the force in this direction is the Hamiltonian, and the force in this direction is the momentum. So it's really amazing. Well, with a minus sign, never mind that, okay? So if you simply calculate, and it's a one-line calculation, you calculate the derivative of this minimizing integral as you shift the point to the left-right in the time direction, you discover that the gradient is given by this formula. You never saw this maybe before, but then you just discover that the gradient is given by the formula L minus x dot times L sub x dot. That is the derivative of the action with respect to t at the right end. So that's how the Legendre transform comes out without us having to invent anything, by simply asking the question, what is the analog of force? And when you differentiate S in the up direction, so in the x direction, ds by dx, then we discover that this is given by L sub x dot. L sits, of course, L is kind of the origin of everything, right? Everything comes from L. And so, and the area preservation is a verbatim copy of what I just described. And so anyway, I will give a very concise description of this next time.
Okay. So thank you very much. Very, I love this parallel. So please let's thank Mark for this wonderful lecture. So you can open the microphone, please. Let's join me. So
Thanks.
Thank you.
Thank you.
Very, very inspiring.